off. Okay, sweet. So for the next person that we have here, let me just quickly make you a presenter. There we go. Hey, can you hear us? Are you with us? You're muted right now, but let me just give you a quick intro. So everyone, round of at-home imaginary quiet applause to Vasudev. Did I say that right? All right, cool. I'm going to start pronouncing surnames because I'm clearly not very good at it. A deep dive into BigQuery's role in transforming business. Vasudev is a staff data engineer, Google developer expert, mentor, cloud evangelist, and Admiral Group PLC. So yeah, quite a rap sheet. Yeah, take it away. We still cannot hear you. Nope. I can see your lips move.
Oh, can you hear me now?
Yes, I can hear you now. All right. Are you able to share your screen and everything? Is that fine?
Yeah, I'm just sharing it.
All right. So, yes, the floor is yours, my friend.
Yep. Hello all, and thanks for joining in the session. So this would mostly around discussing the BigQuery capability and how exactly we have solved certain use cases in the past using BigQuery. So a quick hands up or a message, whoever used BigQuery in the past. Okay, so I have two screens to view the chat as well, no worries. So in today's entire session, we will see about what is the main aim of using BigQuery across your organization or any personal project or any particular, let's say, use case. So we'll walk through each one of the aspect, and I'll start with one of the use case which I have tried to solve in the last particular company or role, wherein how exactly BigQuery helped in the overall business and also contributed to the revenue spike and other KPIs. So moving on to me, I work as a staff engineer at Admiral. So Admiral is a insurance firm. It operates mostly in the UK, and also a GDE and mentor at Google Summer of Code. So starting with a particular use case. So this was based upon a retail giant based in UK. So I couldn't reveal the name due to some confidentiality, but yeah, it operates as a FCMG, sorry, FMCG, and as a apparel brand here in the UK. So the main background was traditionally from last 20 or 30 years they have been operating on a self-managed server, and they have multiple suppliers and distributed data where they want to connect to. And the other pain points was lack of source of truth and high latency when they want to get the data from cloud, sorry, from on-prem to cloud. And there is a lot of latency when they actually want to build something. Let's say if they want to integrate a new supplier to their system. So there is a lot of turnaround time, like 3 or 4 months to onboard the supplier and get the data from uh, on-prem and then migrate to cloud and then use it for reporting and analytics purpose. And if you ever worked in a data engineering setup or an ML setup, so there is a lot of data reconciliation that happens over the time, and there would be a lot of backlog of the data when we actually don't manage it in the most optimized way. So then we have evaluated multiple services like Snowflake, BigQuery, and other similar services as well. So the reason we went with BigQuery is the client was already heavily invested in Google Cloud, and also some out of the box features which we would discuss over the next phase of this session. So the amount of queries which actually comes on that particular BigQuery instance once we have deployed is around 6.5 million per week, and the data size is around 2 petabyte, and now it's near to 3 petabyte, and per week there is a scan of 25 TB of data, and I mean, the initial billing without an optimized way of implementation was around $40,000 per month. So considering all this, I mean, it's a big client, and we had like many problems where or the opportunities to solve. And I would discuss about the considerations and also what are the steps we have taken in order to make it very optimized over the course of time. So when evaluating any platform, things we consider is skills, cost, scalability, security, operations, performance, and community. So operations, cost, and scalability is respective to the any cloud provider or any OLAP system provider. However, skills and community is something which resonates with the amount of support it has in the open source market or the adoption rate. So these were the factors we have evaluated the tool on. And let's say why BigQuery. So if you ever worked on it, it's purely serverless and managed by Google Cloud and fast SQL. So any SQL dialect is compatible and it has its own SQL dialect too. So security, so it tightly binds with other cloud services and other Google Cloud products, and with a native security, and it's actually compliant with GDPR, HIPAA, and other major regulations. And scalability, data encryption by default, like in the transit, in the storage, when it moves cross region, cross zone, and managed storage. Yep. So everything is managed in BigQuery, where we can directly save the data, be it short term, long term. So flexible pricing, we will discuss about the pricing and what is the strategy which we have adopted to bring down the costs from 40K to it's around 26K at this point. We are expecting it to be lesser after June. So, and some advanced features. So the main difference between the traditional RDBMS versus a OLAP system, in this case BigQuery, is the storage type is different. So from the row-based storage, we are moving to a column-based storage where the indexes and the hash maps internally physical to the disk is built upon a column-based storage. So just a quick view, a very high level view on the architecture. So how exactly it works. So back in 2004 and 5, there was a research paper released related to Dremel and Colossus, wherein from Google, wherein it describes about the internal storage and the compute which Google uses for their applications. So it was all started back then. So Colossus is a distributed storage where the data is saved on a physical disk, and Dermal is a high available compute. So behind the scenes, everything works as a distributed and parallel computing, and we will see what exactly servers and how they are made up of in the next few slides. So whenever we actually run a query on top of BigQuery via Python SDK, REST API, or from the console, it actually talks to uh, Colossus to get the data and connect it via a gigabyte network, which is known as Jupyter, and then bring that entire like compute and run the entire queries on the dermal. So this actually gives us a flexibility to separate out the storage and compute. So this is a principle or a thumb rule which is followed by many other OLAP systems in the market, like Snowflake and uh, let's say Azure Synapse. So all these work on the principle of distributing or making the independent storage and independent compute. So let's dive in the quick concepts before we deep dive into the actual best practices. At the end of the session, I would also discuss about new releases with BigQuery in the cloud next, and also a interesting demo on data canvas, which is still in pre-GA, but I've just made a quick demo on that yesterday. So some quick concepts. Let's say if you are new to BigQuery, so we have the entire setup or the entire folder structure of the BigQuery as follows. So we have a GCP project, and then we have a BigQuery datasets. In BigQuery datasets, we can have tables, views, stored procedures, saved queries, notebooks, and all of that. So at a high level, the core components are a GCP project, and then a dataset, and then this is a particular table. So this can have tables and views, partition tables, sharded tables, store procedures, everything as part of a particular project. So this is the project, and this is the data set, and this is the table name. So comes to terminology. So slot is nothing but, let's say, whenever we shoot a query, we want to run that particular query. And so let's say if I want to select certain data from a table, it needs certain level of compute power to execute that query and get back the results. So in a very minute or granular level, the atomic component to actually run that query or support, let's say, RAM or compute power, is known as a slot. So whenever we subscribe to certain slots or whenever we run query, so we actually get the slot consumption time and also the query runtime. So slot consumption time is nothing but the amount of slots it has used to run a particular query. So whenever we shoot a query, it actually parallelizes the entire query on the data and gets back the response. So the slot consumption time is different from the query execution time. And job is nothing but any load, extract, scheduled job, or any routine which has been scheduled on demand or at a cadence, or a query which we run. Everything is known as a job, and job comes with its own unique job ID. And we have on demand and editions pricing. So let's say if I'm a standalone user and I use around, let's say, 5 TB of data query per month. In that case, it's good to only use on demand. And editions is where we actually subscribe to a particular GCP commitment, stating that for next 12 months or next 3 years, I need a constant load of, let's say, 1,000 slots or 2,000 slots. How exactly this works, we will see in the next few slides. And active and long-term storage. So let's say there would be some regulations where we want to keep the data above and beyond 3 years, 7 years, based upon the regulation. So generally, in our case, we keep it the data for 7 long years before retaining the data or archiving the data. So in that case, we might need to go ahead with active storage and long-term storage. So the active storage is nothing but whatever the data which we want to query within 90 days or in 90 days, that terms as active storage, and the long-term storage is beyond 90 days. So any data point which has been saved on a physical disk in BigQuery and doesn't access more than 90 days can be termed as a long-term storage. So this again gives us an edge on utilizing this concept to reduce the overall cost and increase the overall execution time and decrease the latency of the query execution by partitioning the data. We'll see that next. So also partitions, cluster, sharding. So these are the generic concepts across multiple databases and OLTP and OLAP systems. So partitions is partitioning the entire data set by date or any other definitive column. And clusters is something which we'll see where, let's say, if we want to uh, provide a particular table for the reporting purpose from Looker or Tableau, and we want to get the entire data. And let's say if my users are querying the data based upon certain filters 90 or 95% of the times, then I put um, a clustering on top of those columns. So let's say if I want to filter my data by product or subcategory, in that case, I can put a cluster column as product and then get that results filtered in a less latency and in that would be more optimized way, because we are kind of not accessing the data which is not in the other cluster, or let's say in the other product. So sharding is something which we'll see as well, and when it is used, and logical storage and physical storage. So recently, around a couple of years back, Google introduced something called compression of the data, wherein, let's say, if there is a particular logical storage where the data is built as uncompressed data, and in physical storage, data is built as compressed data. So this again ties up, or at some level overrides with the long-term storage and the active storage. So this is the example for slots. So let's say my organization needs around in next 3 years needs around minimum 1,000 slot commitments. So how do I define what is a slot and how do I decide that number? So let's say I do a test run of my entire load from the different departments, and I understand from a, let's say 2 week or 3 week analysis that the capacity which I need would be 1,000 slots. And let's say if there is a product node roadmap or releases over the time where the query load would be increased, like in the next year or next quarter, in that case, I would do an approximation of plus or minus slots, let's say 100 slots, and commit for that. So it's, when I say commitment, we can, as a organization administrator, we can go to reservations in the BigQuery console and then commit for 1,000 slots. So now this slots has been committed, and this can be a breakdown into number of reservations. So let's say in an organization we have data science team, end user team, and the core data engineering team. Now I want to distribute these entire slots into multiple chunks. So then I'll create a reservation. So in this case, in this example, we have 500 slots, 300 slots, and 200 slots. So let's say now I want to assign certain projects to a reservation, then it's known as assignments. So let's say if I use a DS project A in order to execute a query, so the entire slots which is used to execute that query is from the DS. And let's say in any case, I exhaust more than 500 slots and there are any other available slots in ELT or BI. So that would be automatically exchanged with the other reservations. So in this way, we can actually distribute or break down the slot usage. And this would also save us from spiking out the entire queries from a single project. So, and in our organization, what we do is we break down the usage by departments. And because let's say as a core engineering group, if we take the entire cost of the end user group, so that's a lot on the cost center perspective for our department. So we break down the entire reservations with respect to the departments and the end user groups they use. So let's say finance and people analytics. So we actually break that down into that level and move the data to move the slots and commit to the certain projects of the end user group. So let's say if the looker report uses a certain project, so that would be uh, coming into a BI and it would be allocated to 200 slots. And apart from this, on top of this, so let's say for every month, uh, every first of the month, I want to generate some 100 reports and send it to the target users. In that case, there would be a steep spike for every month. So in that case, I can create a max auto scaling slots. So what that means is every month, there should be a additional capacity in a case where it sees a steep growth that can be consumed. So let's say the first step is to alert this reservations with certain slots. And the next step is, let's say if it exhausts 200 slots to generate report, it can actually borrow the free slots from the other reservations. And over that, if that is also exhausted and the slot usage is more than 1,000 or up to 1,000, then I can set a max auto scaling slots limit as one more 100, and that 100 slots would be used as reservations. So this is something which we have used extensively to optimize the initial use case which I have discussed, to cut down the cost and increase the efficiency of usage of the compute. So this is how the editions pricing work, and on-demand pricing works based upon the amount of data which we query, but that is not suitable in an organizational setup because the commitment or the amount of data is more. In our case, in the use case, it was around 25 TB per week, which sums up to the 100 TB or more than that per month approximately. So in that case, we compared the on-demand pricing versus editions. So that in that comparison, the on-demand pricing is more because uh, the costing of BigQuery is based upon the amount of data scanned in terms of terabytes uh, in the on-demand pricing. So this is how the pricing works. So whenever you want to design a pricing model for your BigQuery usage, So you might consider this and you might think in this direction to optimize the cost. So let's come to the next concept of big frames. So this is not the core BigQuery concept. So the core BigQuery concept is something which we have seen in the terminology. So this is an addition which has been added in the last year Google Cloud Next, which is called big frames, BigQuery data frames. So in an ideal world, what do we exactly do? So we have the data, let's say in BigQuery or any other OLAP system. So we read that data into a data frame using Python. And after creating the data frame, then I'll join the data or do some data transformations and then create some metrics. So metrics and features and all that follow. And then I'll create a model. So let's say this is the usual flow. So let's say with big frames, what exactly is an additional advantage we have? So in this case, we would need the entire local computer, local memory, or any other cloud instance for that matter. So it's a managed local compute and local memory. So let's say if I create a Vertex notebook or a Jupyter notebook on my system and read the data, so I need to manage that compute. And let's say oftentimes we see a memory out of issue, like memory out of error and all the infrastructure related errors. And the ease of development is also not in place because we need, so there are multiple touch points. So I understand this is a traditional process which the industry follows. I mean, not the entire 100% of it, but at least more than 50% of the industry follows this pattern. However, there are multiple checkpoints where we are getting the data out of BigQuery. That means we are not utilizing the entire capability of BigQuery which it is made for to run the particular queries in a less latency way and high optimized way. So we are bringing out the data and then utilizing Python to actually run the business logic. So here there are certain aspects to note. So we are bringing the data out of BigQuery. So in that case, there might be some security issues over the transit and the data which we save. And once the data is out of BigQuery, the control which we put on top of that data is lost. So let's say if I have Colibra or Alation or Dataplex, any specific governance tool, and when I bring the data out of, let's say BigQuery, I couldn't enforce those policies until the data goes back in again. And let's say if there is any governance glitch that happens across the medium, I could not enforce my policies on that. So I keep I mean the track would on that particular governance process is lost. So this is one perspective to look at it, and the other perspective is the latency or not utilizing the BigQuery as a whole significantly is one more perspective when we want to build on top of data framework metrics. I mean the other debate is that BigQuery doesn't have the capability to perform what pandas or let's say sklearn does. Yes, that is understandable. So in so with big frames, it solves the gap between pandas, scikit-learn, Python, and BigQuery. So let's see how. So as we discussed, the challenges is limited data, limited compute, and governance issues. So that in big frames, so they have built a wrapper on top of pandas, sklearn, and I guess in preview there is also ml.llm available. So wherein we can utilize all the not all but around 70 or 80% of the entire pandas let's say methods on top of big frames. So how exactly it works is, let's say if I run a command with pandas, so df.filter column a column b, so that would run on top of the data frame. In the same way, I can also run the same command with big frames. So let's say big frames df dot filter column a column b with, let's say, sorting. So now that that big frames command, which is syntactically similar to pandas, translates that to a query and runs on top of a BigQuery as a job. So it translates to a SQL query and runs on a job and gets back the result and shows as a data frame. So from the user perspective, they are still using pandas, sklearn, and they are using ml.llm. So the only difference is behind the scenes, where it has been abstracted at a level of pandas, because pandas is widely accepted and adopted framework across. So we can still use pandas, similar syntax. Uh, Now, from the infrastructure perspective, the entire heavy lifting is taken care by BigQuery. And let's say if my organization is heavily already invested in BigQuery, in that case, I can go this route to utilize the existing investment and utilize the existing slots and utilizing the existing capacity to run my queries and get back the response. So that is the edge of using big frames. And in the recent Cloud Next, it has been made as generally available. You can try it out. There are around 700 plus pandas functions available across the big frames library, and you can directly use on top of any data set available in BigQuery. So moving ahead, BigQuery Omni. So in BigQuery Omni, so in the use case which we were trying to solve, certain level of data was on Azure Blob Storage, and due to the restriction or the type of the data, we couldn't move that data back. So I mean, we explored multiple use cases like Anthos or using a service mesh to get the data or move the data using storage transfer service and everything, but it was costly. So then we realized, why not use BigQuery Omni, which is like multi-cloud querying capability, in short, from the developer's perspective. So we have multiple cloud regions like AWS and Azure. So let's say if we query on top of a Google Cloud region, it would again translate that query on top of the BigQuery compute cluster, which is hosted in AWS. So again, the BigQuery compute cluster hosted across the Azure and AWS is abstracted, and we may not actually worry about that. So we just query it and we get the data directly from AWS and Azure. So this is how a typical flow works. So user queries the data, and the BigQuery control plane, which is nothing but the BigQuery SQL parser on Google Cloud, would actually sense that query on top of the BigQuery data plane on the different cloud platform. And let's say S3 or Azure Blob, it gets the data from that. And then it runs the query job and returns the response to BigQuery control plane and gets back the response to the user. So again, from the user perspective, it's everything is abstracted. I'm just interacting with my data, which is on top of Google Cloud, but I can still access Azure or AWS behind the scenes. So again, the at the end of the day, I'm not moving my data from Azure and AWS. So it comes with the transport layer security, SSL and TLS. So that is widely accepted, security standard across multiple organizations. However, there are certain confidential like computing requirements across multiple organizations like defense and banking. In that case, this might not be applicable. So this is the example use case. So let's say if my operational data is in AWS, and if my transactional data and logs data is in Azure in a hypothetical case, and POS data, and in the GCP we have all the OLAP data. So before or without Omni, so this was in our case. So without Omni, what we had to do is we need to get the data in a presentable way and then combine it and then make a report out of it. However, in the case of Omni, we get the entire data from multiple streams as a single pane of mirror and then build reports on top of it directly. So that is something which is possible with the Omni. So then data clean rooms. So data clean rooms is nothing but in an organization setup or any project, there are multiple requirements to share the data across. So in the case of retail example, which I have taken, so there was a requirement to share the data with the suppliers and the distributors. So let's say we want to do a demand forecasting. Once the demand forecasting is done, we want to share that forecast results with the suppliers so that they can fulfill our demand. So this was the simple problem statement in the use case. So how exactly that was addressed? So initially, I mean, when we haven't migrated to BigQuery, so the users used to download the Excel and share it right away. So there were certain cases where the sensitive details have been shared, because again, humans have a tendency to do manual errors sometimes, so that is acceptable. But however, that compromise certain sensitive data, and it has also in the auditing, it has gone to the regulations and everything, but that's a different story. But the solution which we have tried to address it is mainly using data clean rooms. So we used to have the data contributor project and subscriber project. In the contributor project, we used to create an authorized view, and on top of that, we used to run a DLP scan on the native table. So once the DLP scan is successfully run, so DLP scan would restrict all the sensitive data and PII data based upon a template. So now the entire data is published to a clean room. So now for this clean room, a subscriber would be subscribing to use this. So that means there are two actors in this, and a middleman to serve both the actors is nothing but the analytics hub or a clean. In the analytics club, sorry, hub, there is a concept called clean room, where the clean room acts as a you know middleman to actually get the data from the subscriber and the contributor, and then perform analytics or weave the data on top of it. So this is how the clean room helps in an organization setup to uh, share the data across the third parties or internal uh, you know secondary departments across, or any sister companies if needed. So this is the main agenda behind using data clean rooms. So first we create a clean room and then share the authorized view or data set, and then we subscribe a project to this clean room. In such case, whoever have the access to this project can access the clean room. So then comes best practices. I'll just rush as I'm in short of time. So how do we choose the correct product? How do we cap on compute usage of pa- partitions and clusters? So we need to fix the max slots. So whenever we actually assess the entire capability or capacity needed for in order to run the queries, so there is a trade-off again. So cost versus latency. So I mean, the general feedback which I listen across my team or the end user team is our pipelines takes more than 10 or 20 minutes to run. Yes, that's a considerable time until it's under the defined SLO or SLA. However, let's say if they want to reduce the time further, they can, but it actually impacts the cost, because we have a fixed slots allocated, and that slots are allocated to reservations to certain projects. So in that case, the auto scaling and max slots number should be defined with the right trade-off, and then per project quotas. So that's nothing but, so let's say if I'm an analyst and I want to query the entire database. Now, in case of BigQuery, um, let's say as a user, if I query around 20 TB of data unknowingly every time, in that case, it would cost me more in case of on-demand pricing. So I need to put a cap on the user usage, like let's say 32 TB per day or 64 TB per day based upon the user role. Let's say as an analyst, I might need higher. As a data engineer, I might not need higher usage. So capping the user can also reduce the cost. And monitoring and alerting for checking the ad hoc events, whether there are any deviations in the usage. And then usage of partitions. So whenever we want to use the data uh, for let's say 10 long years, or we want to categorize the data based upon the date, the best practice is using uh, the data, like partitioning the data based upon the date column. Or I mean, there are multiple partition rules. So a generic partition column which we tend to use is date column. And clustering, based upon the filters, we can use that. So sharding is nothing but, like, there is a limitation in BigQuery where we can't use partitions more than 4,000 on the native tables. So in that case, sharding the tables with the suffix would be helpful. Uh, and then monitor. So we can use the monitoring tab, and we can put the alert on costs and also auto scaling. So I'm just rushing because I want to show you a demo. So storage strategies. So let's say if there are any data points which needed to be shifted. So let's say after 7 years, I don't need any data on BigQuery. So we can directly shift it to a cold line GCS bucket so that we can save on cost. Use compressed storage. So this would also reduce the cost by 1/3. I mean, this is tried and tested in our case. So then, sorry, we have cleanup and storage. So oftentimes in big organizations, so there is a tendency of housekeeping of the entire BigQuery. So if they doesn't do that, there might be certain unused storage which is going into waste, like let's say experimentation and everything. So what's new with BigQuery? So these are some of the announcements in Google Cloud Next, and this is nothing to do with the earlier use case. So real-time analytics. So we have a PubSub. Uh, let's say we have a PubSub, and PubSub topic directly gets the data messages to the BigQuery, and BigQuery continuously runs or performs transformations on that data. So that is now possible, and this is in the trusted testing program phase right now. It's not yet GA. So we can assign a slot permanently to the real-time streaming source, and then in BigQuery can transform the data using that slot compute, and then sends that data to the downstream. And then we have BigQuery workflows. So this is again preview where I can create the workflows one after the other from. So this is for the execution from the no code perspective. And then we have Gemini. It's now integrated. So if you want to try it out, please do. So till July 11th, I guess it is free to use. And there is no cost to use Gemini in BigQuery. So it can be used to generate a SQL query, or used to understand the results, or use or to do a keyword search across the projects. And then we have data canvas. This is again a no-code solution. Let's say if I don't know SQL query or SQL language, how do I do a quick analysis of my data? So this is again on preview. Then data preparation. So this is not yet released. So this is for preview probably in Q3 24. In this particular part, we can cleanse the data, understand the data, analyze the data, and let's say if we want to do some derived columns, we can do that and directly translate that to SQL. So that is possible with this. So I'll just move to the query. I guess I have a couple of minutes now. Yeah. So here I have just used Gemini to. Sorry, can you see my screen? Yeah, I guess yes. So this is the prompt which I have given. So and so this particular Gemini, with this prompt, it generates me a code, kind of SQL query. So this is a SQL query in order to get the products starting with letter I. So however, I mean, at this point, Google suggests to recheck the generated output as it is in the trusted testing program. However, this actually is useful to generate the queries. And the next is demo canvas, canvas, data canvas. So I've just used the canvas to understand and do a quick experimentation. So here we have orders, and here we have inventory items. So these are the two data sets out of the LookCommerce public BigQuery dataset. And once we create this, we can now join the data or query the data. So here I have just joined the data. So how exactly I joined it? I have again given a prompt. So this is the prompt which I've given: inner join on order ID from orders table and ID from inventory items table. So this is the prompt, and it generated this code, this particular SQL query. And this is the mid step. And let's say then I want to understand, I want to perform one more operation. I mean, this is just for example purpose. I can do all this in a single query as well. But so count the orders by product type and the count, and then sort the results by descending order. So it then generates this result, and it gives me this. So now in the visualization, so this can be created manual or again with the Gemini. So create a bar chart and sort the order value in descending. So now it then creates a bar chart and it aligns in the descending. So now you can try this out, and this is also free to use. And one good feature which I've seen is export as notebook. So now when we export this as notebook, which I've already done, it would be directly translated to Jupyter notebook. So all the queries is translated to Jupyter notebook, including the charts. So this can be used for a rapid experimentation of data analysis. And now at this point, the data canvas is evolving. You can use it and give the valuable user feedback via the email, or which is mentioned by clicking the submit feedback. And as a whole, you can again use Gemini for auto generation, code generation, explanation. So this is, as I understand from the documentation, it is free till July 11th. So you can try it out. And yep, so that's all from my side. Sorry for being a bit faster. And if I have some time, you can ask me any questions. So you can connect with LinkedIn if you have further questions on this. Thank you. You're on mute, Mike. Sorry. Yeah, I can hear you now.
I don't know what happened. It decided to connect to my webcam microphone, which is also always off. Right. So I was saying that thank you very much, and sorry to have delayed you at the beginning. Um, there seems to also be a delay between the video, the live stream, and the chat. So if there are any questions, once again, folks, you have the QR code and the LinkedIn over there. So don't be shy to reach out and to ask our lovely speaker questions. But yeah, thank you very much.
Yep. Thank you. Thank